So, we are at lecture number 10. This is week 2. So, I thought at the end of every week there is a tutorial. So, this is the second tutorial for the second week. So, in this tutorial we are going to solve some of the examples, right. Some of them have appeared in the previous GATE examination. So, here for example, here the example number 1. So, Waterbirds technique to determine when to give irrigation. So, this is the problem. So, in this, so what are the given things are? There is a daily ET and PE of the following table. So, table is given. So, in this table, so the month of July, the first, second, third, fourth, fifth, sixth, seventh, 8th days, like 8 days. So, each day what is evapotranspiration? So, IN is the inches. Okay. So, these are the units are in inches and P is this is effective precipitation. So, the mostly this is I mean the amount of precipitation which has contributed to soil moisture. So, that is that precipitation also given in inches. Okay. So, depth units, right. So, and root zone depth is given 24 inch, right. You have root zone of 24 inch. Suppose this is the RD. So, sorry DRZ. So, that is 24 inch, and the soil water content on the morning of July 1st is 23%. So, here, so in the morning there is a 23% soil moisture was measured, okay, and this is on volume basis, and but theta c is 14%. So, our interest is, so when this 23% is reducing to 14%, so then you give irrigation. Okay. So, theta c here is your threshold, right. So, with this criteria, so find out what is the data of next irrigation. So, this is the question, right. So, you got some table of data and root zone depth is given, and there are two soil. So, initial soil moisture is given, and then when to start in irrigation. So, the theta c, the threshold moisture content 14% is given. So, based on this data, so when the irrigation is needed. Okay. So, the solution here is, if you see the solution here, the sample calculation for day 1. So, you have seen this equation just in the previous lecture. So, for any day's soil moisture theta I is equal to previous day soil moisture minus ET minus effective precipitation divided by root zone depth multiplied by 100. So, that will give the moisture content under a particular day, the current day. So, with this data, so 23 is the initial, so day 1 moisture content. So, that is 23%, and then exactly not day 1. So, just before day 1, and then ET is given in that particular day. So, that is 0.33 minus, so precipitation is 0, right, and this is root zone depth 24, and if you do this math you get 21.63. So, that is the soil moisture day 1 is 21.63. So, then if you follow this calculations, right, in the day 2. So, this is your initial moisture content like 23 here. So, this is your theta I minus 1, and then use this ET, this PE, and then you can estimate theta I here like theta 2. Okay. Now, for the similarly theta 3, theta 4. So, it goes like this. Okay. And then, so what is your triggered like theta c? So, theta c which is equal to, I think that is a 14% if I remember correctly. So, if you go back, just go back, let me see. Okay. So, this is 14%, right. So, the 14%, and then so look at here. So, let us check, this is 15% and 13.8%. Okay. So, exactly, so this is almost equal to 14% and you give irrigation at 8th day. So, that is July 8th is your irrigation day. So, and then the so how much really you need to apply on 8th day. So, amount of apply for irrigation, so which is I equal to, so this theta f c minus theta into root zone depth divided by E I, that is efficiency, irrigation efficiency. So, let us assume this 80% irrigation efficiency, okay, and theta is the percentage of water content soil prior to irrigation. So, prior to irrigation you have to see, let us see 15.05, okay, and then 26 we assume this field capacity. So, it is, I think it is given, if it is not given let us assume. So, this is 26% of field capacity F c, okay, and then 24 root zone, and this is efficiency, and you get 3.29 inches of irrigation you have to apply on July 8th morning. Okay. So, that way you can, so this example clearly gives how to give irrigation, not how to give irrigation, but at least when to give irrigation, how much to give irrigation. Okay. So, the next example here, suppose you have 50 kilometer long canal, right, you have canal length 50 kilometer long canal, okay, and it has a width of 25 meter. So, this is 50 kilometer canal and 25 meter, this is the length used for irrigation. So, this is being used for irrigation. So, the mean daily evaporation as measured from class A pan evaporation pan is 5 mm per day. So, here let us say there is a pan which is installed nearby that gives 5 mm per day, okay, 5 mm per day, that is the evaporation every day. So, 5 mm per day, and considering the pan coefficient 0.8, the mean daily evaporation loss from the canal is, okay. So, as I said, so this is installed adjacent to this canal, right. So, the evaporation from the pan evaporometer is not same as the evaporation from the reservoir or the canal. So, if you can multiply this the pan evaporation with pan coefficient 0.8, right, you get the evaporation from the canal, right. So, knowing the evaporation from canal and area, you can find out, you can find out the how much water really you need to deliver from the canal, so that it can meet the irrigation requirement. So, the length of canal here, the class A pan 5 mm, so pan coefficient this much, and area of canal, this is area of canal, and mean daily evaporation loss. So, this will give I mean this portion will give the lake evaporation, right, lake evaporation. This is pan evaporation multiplied by 0.8 coefficient lake evaporation. So, that means the nearby water body evaporation, and this is the depth and this is the area, you get volume. Okay. So, this is the volume per day. So, daily you have to release this much water in order to meet the irrigation requirement of the crop. Okay. So, then the third example here is the soil moisture at field capacity F c is 25% weight basis, okay, and the soil moisture at time of irrigation is 15%, it is also weight basis. The apparent specific gravity, that is 1.25, that means the density of soil divided by the density of water. So, that is apparent specific gravity 1.25, and the depth of soil to be wetted is 40 centimeter. Okay, the depth of soil to be wetted 40 centimeter. This is kind of root zone depth. Then how much water in hectare centimeter per hectare must be applied. So, that means volume of water you need to apply, how much volume of water you need to apply. So, this is very simple. If you think about like field capacity, that is 25%, this weight basis. So, converting weight basis to volume basis, you need to multiply with the apparent specific gravity or bulk density of soil. So, the moisture content field capacity, so 25 field capacity weight basis multiplied by apparent specific gravity, you get 31.25%. This is the volume basis. So, similarly, the moisture content at irrigation time SMA, let us say 15%, convert that into volume basis. Okay. So, you got moisture content field capacity, moisture content irrigation time in volume basis. Okay. And the depth of soil to be wetted is 40 centimeter, this is the 40 centimeter depth needs to be wetted. The water depth required to fill field capacity. Okay. So, if this is the moisture content and this is the field capacity, so the difference you need to apply, okay, difference need to apply multiplied by the D, okay, and you get this is the volume basis and 40 is the depth, okay, 5 centimeter. So, 5 centimeter of water you need to apply on the surface. So, that will be sufficient to wet 40 centimeter of soil, right. So, then water required depth per hectare. So, that is simply you have to multiply with 1 hectare. Okay. So, 5 hectare centimeter is the answer. Okay. So, 1 unit 5 centimeter for 1 hectare into 5 centimeter. So, this will give the volume of water needs to be applied on the field. So, that 40 centimeter of the soil is going to be wet. So, this is this is third example, and the fourth example, if you look at. So, here potato crop we are looking irrigated with water having an electrical conductivity of 1.1 decisiemens per meter. Okay. So, this is 1.1. So, Siemens, so it is measured in Siemens. So, this is decisiemens and the application efficiency is 70%. The seasonal crop evapotranspiration and seasonal rainfall are 350 mm and 125 mm respectively. Okay. Crop evapotranspiration and rainfall, this is crop evapotranspiration and this is rainfall. So, average soil salinity tolerated by the crop is 1.6 decisiemens per meter. Okay. So, this is tolerance, crop tolerance, salinity tolerance, and the seasonal irrigation requirement is, how much is the seasonal irrigation requirement. So, here remember, so the irrigation is required not only for crop and also for the salts to be leached down. Okay. So, the double, I mean you have to apply more water in this. So, that is why the equation here, the seasonal irrigation water requirement, the equation if you see. So, this is for crop, right. So, multiplying 1 you get to give the crop, and the LR, the leaching requirement, multiplying this amount through LR for the leaching requirement. So, it has 2 parts. So, the ET minus PC, so this is the demand, right, and this is what we got it from atmosphere. So, the difference you need to apply. So, the difference you need to apply for the crop as well as for leachate requirement, okay, and EA is the efficiency. So, the leaching requirement, if you recall the equation from the previous exam, lectures. So, this is ECW, so that is salts present in the irrigation water divided by 5 times ECT. So, this is crop tolerance minus ECW, electrical conductivity of water. So, here based on the data given, 1.1 is EC, right, in the irrigation water, and 1.6 is crop tolerance, Okay, so then you get leachate requirement 0.16. So the seasonal irrigation requirement here using this equation, right. So 350 is ET and 125 is effective rainfall. So then the difference is the irrigation amount you have to apply, and for crop and for leachate requirement. So the total amount of irrigation water you need to apply is 372.86 mm. Okay. And then, so the next is though it is showing big, but it is okay. So a checkbook a check basin of size 15 meter by 12 meter. So we are going to talk about the basins in the next next lectures. So 15 meter by, so there is a check basin which has 15 meter long and 12 meter wide. Okay. So irrigated using a stream of 26 liter per second. The depth of crop root zone 1.3 meter. The apparent specific gravity of the root zone is 1.6. The water holding capacity 16%, okay, that is field capacity, and irrigation is to be applied when the soil moisture content in the crop root zone attains to 12%. So, this is our threshold, and deep percolation loss is neglected, no deep percolation loss. So, determine the net irrigation requirement in mm, okay, and the duration of the irrigation in minutes to replenish the field capacitor. So, in this example you need to find out the irrigation amount and when to give in irrigation. So, both time and amount you have to find out. Okay. So, this is an example of perfect irrigation scheduling method. So, because here also check basin is the method of irrigations, how how to give irrigation. Okay. So, the solution here, so the given data is like this, the discharge is 26 liter per second. So, that is 26 you convert into meter cube per second, and area of check basin 15 to 20 12, depth of crop root zone. So, you have a depth also, so that is 1.3 meter, and apparent specific gravity. So, that is rho is given 1.6. Apparent specific gravity, okay, it is not rho bulk, not bulk density. So, let us say this is gamma, okay, this is a gamma, and water holding capacity of soil 16%, soil moisture content 12%. So, this field capacity and theta c are given, right. So, then the solution here for this problem is like this. So, first thing is we have to find out what is depth of irrigation, and then finally the duration of irrigation. Okay. So, here the depth, amount, the quantity, and here the time, the duration. So, if you recall the equation, theta f c minus theta, right, c multiplied by apparent specific gravity, okay, apparent specific gravity, let us say, and then root zone depth d r z divided by 100. So, put the values, theta f c is given, theta c is given, all values are given, and you get the net irrigation requirement is 83.2 mm, and the discharge here is equal to area, this net irrigation requirement by time. So, this is the discharge formula. So, discharge is given 26 in 10 power minus 3, area is given, we calculated this, and time. So, you have to find out this time. So, it is very simple. So, from that putting the values together, and you get the time as 9.6 minutes. Okay. Okay. So, this last example is So, in this a bean crop is grown in clay loam soil and is completely developed. Okay. So, the groundwater table is more than 10 meter below the surface. Okay. So, that means it will tell whether the groundwater is contributing to soil moisture or not. At the beginning of mid season stage of crop, the moisture content is a field capacity. Okay. So, mid season case, so it started with field capacity, that means just they gave irrigation. Okay. So, the reference crop evapotranspiration and percolation values of 10-day period are given below. So, this table will give, so the 10 days period, right, and then ETZ, ET0, the reference evapotranspiration, and then the P value. So, that is precipitation values are given. So, using the above information, develop irrigation schedule based on fixed interval of week and MAD. Okay. So, every weekly irrigation intervals and also based on the MAD. MAD is manageable allowable deficiency. So, let us see how this problem is being solved. So, the solution here includes, so assume no runoff occurs during the precipitation event, because that is the number one assumption we think of. So, that means the intensity of rainfall is less than the infiltration rate. So, that means the rainfall there is no runoff. So, whatever rainfall which is falling, that is going to be effective. Okay. So, that means used for the soil moisture contribution. So, then bean crop is fully developed at the beginning of mid season stage, and thus root system is also fully developed. So, we are not going to include dynamic root zone depth here. So, that means it is fully developed. So, we are taking the full root zone depth in this case. So, for bean crop, effective root zone depth is 6 centimeter and Kc mid 1.5 centimeter. If you recall the table in the previous lectures. So, the Kc mid 1.05 and root zone depth 60 centimeter, and these are the literature data. From clay loam soil, theta Fc is 36%, wilting point is 18% and MAD is 0.5, right, 50% depletion. Okay. So, with this information you can find out total available water, which is theta Fc minus theta wilting point into root zone depth. So, if they are all volumetric basis, then you need not multiply with apparent specific gravity. So, 0.36 minus 0.8 into 60, you get a 10.80. So, this is the reservoir. Okay. So, this is the reservoir. So, 10.8 centimeter. Then allowable depletion AD. So, the 50% of this we are going to allow like 5.4 centimeter. So, if this reservoir, right, down up to 5.4 centimeter, right, because there is a crop is taking water, and if 10.8 centimeter depletes to 5.4 centimeter, then you give irrigation. Okay. So, and another thing is at the beginning soil moisture at field capacity, thus SMD is equal to 0. So, soil moisture difference is 0 at field capacity, right, difference like delta S you are talking, right. So, delta S is 0 because it is completely reaching to field capacity. Okay. So, this table will show the whole calculations, remember. Okay. So, there are 10 days, I said 10 days period. So, day 1 the soil moisture difference is 0, okay, and ET 0 is given, KCI is Kc because no soil moisture stress. So, we give Ks as 1, right. So, there is no soil moisture stress, that is why it is 1, and Kc 1 we got from the table. Et is given. Okay. So, Et is given in the sense Et 0 is given and multiplied by this Kc and you get etc. Okay. So, then dP, okay, so the P is given, sorry, depercolation is 0, right, because because of what? So, depercolation is assumed as 0. I mean this is already given as 0. I is the rainfall, I is the input, irrigation amount, and Pe is effective precipitation. So, that is given, data is given. So, with this the first day 1 we can estimate this SMD as 5.9. How do you estimate this? You go back and check the equation, right. So, that SMD is equal, this is water balance. So, simple water balance. So, you know ETC is given and P is given, right. So, that difference, okay, and then so our previous examples definitely will give this SMD. So, 5.9, right. So, how do you get 5.9? 5.9 minus PE, so everything. So, this you get this 5.9 is 0 is here. So, take this 5.9 here now. So, this is your new soil moisture deficit. So, then find out this is 5.7 minus everything, right, and then plus 5.9, 5.7 plus 5.9 you get 11.6 and 11.6 comes here, and then you estimate, right, you get 6.2, this is the loss, right. So, 6.2 loss, and then this is the difference 11.6. So, summing up you get 17.7. So, similarly daily you go one by one and finally you get 54.0, right, at the end. For MAD based schedule 5.4 mm of irrigation would be required on the morning of 11th day, whereas irrigation amount would be 36.8 mm after a week. So, if you are talking about 10 days versus 7 days, right. So, 10 days you give 54 mm. So, that is based on MAD, or weekly basis. So, you give 36.8 whenever there is a difference of 36.8 mm, right, you give irrigation. Okay, I think that is it. So, in this tutorial, so we have seen some problems related to irrigation scheduling. So, when to give irrigation and how much to give irrigation, and also the how to use the pan evaporation data for irrigation scheduling, okay, and mostly the tables. So, the water budgeting technique we use for irrigation scheduling. Okay. So, hope go through these examples. This will, we have to practice these examples, so that it will improve your the practicing style. Thank you.